Seminar. This morning, we are going to hear a really fascinating story, I think, about the Central City Tunnel System in Minneapolis. For those of you who do not know, there are a whole lot of stormwater tunnels that collect runoff from nearly all the downtown area of Minneapolis, with some of the tunnels dating back to the 1800s. The City of Minneapolis Public Works Department recently constructed a new parallel storm tunnel 70 feet beneath the city to handle increased stormwater capacity and reduce pressure in the existing stormwater tunnel, one of the largest projects the Surface Water and Sewers Division has ever completed. And this morning, we get to hear about that. Joe Klejwa is a project engineer with Surface Water and Sewers for Minneapolis Public Works, and he's been with the city for 29 years now. He started working for the city of Minneapolis in 1997 and joined the sewers operations team in 2009. He'll be speaking on some of the city's history of collector tunnels and the efforts to fix aging and undersized tunnels. And our second speaker, Kevin Danen, is a registered engineer with 30 years plus experience in engineering. He has worked in private consulting, performing materials testing, geotechnical and environmental drilling, and surveying. Kevin started with the city of Minneapolis in 1997 in the engineering and materials lab, joining the sewer operations team in 2009. Joe and Kevin, it's great to finally have you with us to talk about this really interesting subject. Take it away. The floor, as it were, is yours.
All right. Well, thank you. I'm Kevin. I'll be starting off our presentation today. Joe will be taking the second half of it. So I will get into it. We're here today to talk about, obviously, the Central City Tunnel System. And I'll be talking about how our asset management program led us to the Central City Parallel Tunnel project. First, a little overview of the sewer systems in the city of Minneapolis. We have two separate sewer systems. We have the sanitary sewer system and the storm sewer system. The sanitary system is quite large, 830 miles of sanitary pipe in the city. It ranges anywhere from 6 inches in diameter up to 96 inches in diameter. We've been blessed with mostly a gravity feed system. However, we do have 10 lift stations. The sanitary sewer system dates back to the 1870s when they first started developing the city of Minneapolis. Some of the oldest sanitary sewers we have are in kind of the central core downtown area. The storm system, not quite as large, 565 miles of storm pipe there. It drains over 54 square miles of city area. We've got 23 pump stations to assist us there with the flow. And we've got 400 outfalls. All the stormwater basically, excuse me, drains into our storm sewer system. And then we direct that flow to area creeks, lakes, and of course the Mississippi River. We've got over 30,000 catch basins to help collect all that stormwater and divert it to the tunnels. Speaking of tunnels, we have over 16 miles of tunnels in the city. They're located here on the map in red. Those storm tunnels are responsible for draining approximately 30% of the city. So they do play a large role in the storm sewer system for the city of Minneapolis. The tunnels typically range from 5 to 100 feet deep below the surface. They are located in the St. Peter Sandstone Formation. Tunnels were built between 1882 and 2001, with the majority of them actually being built between 1930 and 1970. We actually have two tunnels that were built in the 1880s that are still in use today. For the mechanics of the tunnels, the concrete, they're made out of concrete, and the concrete liner is typically anywhere from 8 inches to 12 inches thick. They are not reinforced tunnels. There's no reinforcing steel used in the concrete tunnels. They instead rely on the contact with the surrounding sandstone to support them and to withstand the forces that the tunnels are experiencing. It's kind of a key topic here. It's it's kind of been a little bit of a curse when we've had to deal with these tunnels. So how do we manage all these systems that we have in the city? Well, we use the principles of asset management. I'm not going to go into great depth here to talking about asset management because tunnels are way more interesting. Um, but asset management just typically follows an asset through its life cycle, starting with, I got a laser pointer here. Starting with identifying the need for an asset and then constructing it all the way through decommissioning the asset and possibly replacing it or renewing it. Excuse me. Our storm tunnels, like I said, we are following the asset management system here with them. Since most of the tunnels are approaching 100 years old, in some cases they're even older, we're well beyond the construction and commissioning phase for the tunnels. We are kind of in the deterioration and maintenance phase, and also kind of in the performance monitoring phase. So they've been in use for a while, starting to deteriorate a little bit, so we need to monitor that. And following along with asset management, we use what we call a strategic asset management system. We use a risk-based approach to our tunnels in particular, and we also do use that with the rest of our sanitary and storm sewer systems. But today we're talking about tunnels. So we basically use two factors to determine our risk score for our tunnels. Those two factors are likelihood of failure and consequence of failure. Basically, we assign each tunnel a score according to likelihood and consequence of failures, and then we multiply those factors and come up with an overall risk score. And we use that to help us identify where we should focus the work on these tunnel systems. So how do we determine likelihood of failure? We actually go down into the tunnels and we assess the tunnels. We perform a system assessment on it to determine all the defects that are going on in the tunnels and to figure out what their level of severity is. This is what a storm tunnel assessment looks like. We're down there in the tunnels and we're looking at pretty much every square inch of tunnel, identifying every defect that we can, and then we're recording that so we can bring it back to the office and analyze it. When we first started doing this asset management system on the tunnels, we did a complete assessment on all of the tunnels, and it took us, we were part of a team of 4 people, it took us 56 days to inspect all 16.2 miles of tunnels. We've got 22 separate tunnel systems, so that involved a lot of mobilization, setting up cranes, setting up a lot of equipment. Like I said, these are deep tunnels, so we have to get loaded into a basket and lowered down a shaft with the crane. So a lot of work went into just even getting into the tunnels. Over that 56 days, we documented well over 26,000 individual defects over that whole 16.2 miles of tunnel systems that we have. So we ended up coming back with a lot of data. Typical defects that we would see when we were down in the tunnels would be cracks and fractures along the concrete. These tunnels experience a lot of pressure and stress, so the concrete cracks. We would see scouring of the concrete inside the tunnels, a lot of water flow scours the concrete away, kind of weakens that concrete surface a little bit. We'd see some miscellaneous holes in the tunnel liner. Pouring concrete isn't an exact science, so some of the areas of concrete were a little bit thinner, and so they would just wear away or give way over time with the pressures. Here's a section of tunnel invert or the floor of the tunnel, thinner concrete, it eventually just gave way over time, and we ended up with a hole in the bottom of the tunnel. Another typical defect that we might see is groundwater infiltration. The concrete tunnels are poured in sections, and so where there's concrete seams, there's some little weak spots there. So groundwater would eventually find its way into the tunnel here. We've got a gusher, what we call a gusher here. Sometimes there's drippers or weepers. In this case, it's kind of a little more severe than that, so it's a gusher. Um, the tunnels also another kind of interesting fact is the tunnels at that depth, we are in some cases in the groundwater table here with these tunnels. So when they constructed the tunnels, they actually had to de-water and dry up the sandstone, then construct the tunnel, turn the pumps off, and now these tunnels are actually submerged. So that's kind of likelihood of failure. The next factor that we take into consideration with the risk is determining the consequence of failure. This is a little bit easier. Each tunnel has a defined drainage area, so that we know that if that tunnel fails, and by the word fail, I mean it is no longer able to convey flow to the river or the creek or the lake, that will impact a certain defined area. So we're able to look at that area, determine the number of properties that may impact, because that failure will result in basically on-street flooding, which could impact any buildings or structures or people located within that area. Determining consequence of failure is a little bit easier. We don't have to go into the tunnels. We don't have to mobilize forces. It's basically sitting at our desks utilizing GIS, property records, photographs, and kind of determining what the extent of that consequence of failure would be. So we take all that data and we put it together and we come up with that risk score. And with that risk score, we're able to put together a priority list. When we first put this together back in 2009, we had a list of over 51 identified areas in our 22 tunnel systems that really needed to be addressed. Some were very critical, and some were less severe, so we could kind of put them off. So we had all this data, we had estimated costs put together. Here, utilizing my laser pointer, in 2009, the estimated cost of repairing all the deficiencies in our tunnels was about $106 million. A rather significant portion. It was not built into our funding at all. So that was kind of eye-opening to us. We realized we couldn't do it all at once. So we put together a storm tunnel program. We kind of programmed this out, trying to do it in manageable chunks each year, but that was still a significant amount of investment. So I'll talk a little bit later about that. So the very important, real key critical data takeaway that we had was we could take all this data and put it into a program and put it into lists and numbers and stuff like that. But what was really beneficial was we were able to take it and put it into a map like this. This is a very presentable format that we could use and take this to city council and the mayor and the city engineer and even my supervisor and say, you know, we spent a lot of time putting this together. This is what it looks like. This graphic really helps paint the picture. So asset management was very helpful in creating something very simple that we could use to get our message across. As a result of all this data, we could, basically say 22% of our storm tunnels are in poor condition. We need to start addressing them now, because like I said before, these storm tunnels drain 30% of the city, so it is a significant issue. So utilizing asset management, utilizing all those costs, we're able to present that message. Prior to that, our funding levels were not that great. We were often funded at a level below $2 million a year. That was appropriate for us to respond to small local failures. We could get down to the tunnels, patch those little holes, but we couldn't really do anything proactively or even start addressing some of the larger scale defects that we found in the tunnels.
What you doing back there?
So what we did is in 2010, we took that graphic and we started kind of getting out there, kind of getting the communications out there that this is what we're up against. Our funding isn't appropriate. And one key thing that we found out that people were very receptive to is we actually took our city council down into the tunnels and we showed them what we were experiencing and what we were documenting and seeing. Um, this was actually an amazing thing that we did here. The response was so great um, that they bought into it. They recognized the importance and the significance of what we were up against here. So prior to 2009, like I said, our funding was kind of anemic. After we got our message out there, and I don't want to say it just took that one visit. We continuously do this. Every time a new council gets elected to the city of Minneapolis, part of our initiation to them is we get them down into the tunnels to understand that this is an ongoing process here. But back in the day, the response was really great. You can see our funding went from sub $2 million a year up to over $8 million per year. That response, like I said, was so great, and they were giving us so much money that we had problems spending it at the rate that we were being given the money. So in 2015, we actually had to request $0 just so we could catch up with the money that we had been prior supplied with. So that response for us, like I said, worked out really great. So that when the Central City Tunnel project came up, which was many magnitudes greater in the funding requirement, we actually got the governor of Minnesota to come down into our tunnel system. And we were asking for state bond money at that point in time to help us fund it. Kind of the funding level of the city would not have been harmed by supplementing it with state money. So we got the governor down there and everybody was smiles and it was wonderful. And this green line represents the state bond money that we got. So it was a significant boost on top of what we were already receiving. So we could go ahead and do the Central City Tunnel project. So we had all that information. We've got all the support. We've got the money. We started. So in 2011, right away, we kicked off our 10th Avenue Tunnel rehab project. It was 2 miles of tunnel. It took us 6 years to do that work, and we spent well over $10 million on that project. We kind of were getting our feet wet. We felt good about where we were going, so we kicked off the St. Mary's Tunnel rehab project in 2012. Not as long of a tunnel. Didn't require as much money. It wasn't in as bad a shape. So we really started working on those 2 tunnels. I'll say the rehabilitation effort of those 2 tunnels was a little bit more straightforward, not as difficult as the Central City Tunnel system that I'll get into. It was kind of more crack sealing, hole repair. There were some fractures in the concrete that we had to address, but as far as tunnel rehab goes, a little more simple. The next project that was to be completed after 10th and St. Mary's was the Central City Tunnel System, kind of the core of our presentation today. Where is the Central City Tunnel System? It's right here in downtown Minneapolis. It is located basically underneath the core of downtown. It is a 4-mile long tunnel system. We have what we call drift tunnels. They feed into this one main tunnel here that takes all that water and brings it out to the river just below St. Anthony Falls. The drainage area of the Central City Tunnel System, again, it's really located underneath the core area of downtown. So it's a critical tunnel system. Failure on this tunnel system really is not an option we ever want to consider. We do not want this tunnel in a condition where it is not able to convey that flow out to the river, because if that's the case, then we are flooding downtown, and that's not going to look good on us. So the Central City Tunnel System, like I said, it's a little bit different from the other 2 tunnel projects that we had worked on. We've got 2 unique issues with this tunnel system. The first issue is land development, and the second issue that we had to deal with was the construction methodology. So the first one being land development. When this tunnel was first constructed in the 1930s, the downtown area looked a lot different. The use was different. The buildings were different. There were dirt streets in the city of Minneapolis downtown. There were even residential houses in the downtown area. So whenever rain fell downtown, the majority of it could either soak into the ground or, well, the majority of it did soak into the ground. Some residual stormwater was directed to the new Central City tunnel system that was constructed, but the vast majority of it most likely sunk into the ground and did not get conveyed directly to the river. 100 years later, downtown looked much different. Um, a lot of the residential areas were gone. The vast majority of surface area was impervious. So all that rainwater pretty much got directed to the Central City tunnel system now. So that resulted in the Central City tunnel system being overpressurized. It just was not designed to handle that much water. The second unique issue that we have with the Central City tunnel system is the construction methodology. So back in the 1930s, when they constructed the tunnel, they mined out through the sandstone an area sufficient enough for them to work in. They had rail cars going down the tunnels that they would dump the sandstone into and rail it all the way out to the end and then get rid of it from there. They mined it so that they could run communication and electric lines through the tunnel systems, because like I said, this is 4 miles of tunnels that they were building. So they needed lighting and communications down there. And they even mined out enough area to stage some of the materials down there. So the area that they mined out ended up being much larger than the resulting tunnel that stayed in place after they were done. So in order to construct the tunnel, what they would do is they would mine out that large area and then they would come in afterwards and put up all this wood shoring and then use that to support the concrete tunnel liner that they would place afterwards. Here you can see there's two separate pours like I talked about before. They would come in, they would pour the base of the tunnel, and then there would be a joint here and a joint here, and then they'd pour the top of the tunnel. Um, Thick tunnel section, a lot of concrete. So that was probably great at the time. It was really easy to construct. They had this process down. Well, it turns out through our investigations that that construction methodology really kind of came back and bit us a little bit 100 years later. Through our investigations, we found that that wood over 100 years, it was exposed to the air and groundwater and it decayed. Um, This is a picture of a similar area there compared to the previous picture. You can see here's the crown of the old excavation that they had, and here's some of that remaining wood. Here's a better picture. You can see all the wood has deteriorated from around the concrete, and we've got the large void above the tunnel, and we've got the void on the sides of the tunnel where that wood once was. Now, why is that an issue? Like I said, these tunnels are not reinforced. They rely on contact with the surrounding sandstone to withstand their pressures. So once all that wood eroded away and decayed away, there was nothing to support the top or the sides of the tunnel when it pressurized. Back in the 30s, when they first built it, it probably wasn't an issue. The tunnels were not pressurized. This is a good picture of what the tunnels operated like in the 1930s and 1940s. Tunnel's happy. It's not full of water. There's a void above the tunnel, but it's not an issue. As time went on and the city developed and they started directing more stormwater into the tunnels would fill up and pressurize. And since there was no support around the tunnel, primarily in the top area, it would start cracking because the tunnel didn't have that material in contact to withstand those forces or transfer the forces to. So over time, the concrete tunnels would crack, and this is what that looks like. So you can see the two cracks. The top of the tunnel would actually eventually get to the point, in this case, where the top of the tunnel lifted off. There was so much pressure in the tunnel that the concrete lifted off and shifted over a couple inches and came back down. So if you can imagine the forces that are going on in these tunnels, the pressure down there, that there's enough pressure that it lifted this huge slab of concrete up and over. You can begin to understand the pressures that these tunnels are experiencing because we've put so much water into them. Over time, water gets out of these cracks and it starts eroding additional sandstone outside of the tunnel and making these voids larger, thus reducing the ability of the sandstone even more to support the forces outside of the tunnel. What happens when that starts happening is here's a fracture in the top of the tunnel. Water's jetting out over the top of the tunnel, eroding that sandstone and bringing all that sandstone back into the tunnel. This is a 6-foot tunnel. This is, again, located in about the same area that those old time pictures were located in. There's so much sand in the bottom of this tunnel that we now had to duck walk through the tunnel. It was about reduced to about 3 feet. This in turn reduces the capacity of the tunnel, which backs up the storm water towards the street surface. So it causes even yet more pressure in the tunnel. So this is kind of a cycle that we got into here that we really had to correct. Over time, we get to the point where there's complete tunnel liner failure. The void is so big, the concrete has been weakened so much that the concrete just gives way. And then we're kind of in a completely uncontrolled state. The water is outside of the tunnel. It's traveling all up and down the tunnel, eroding sandstone. And now what may have been kind of a localized failure is now a long failure, linearly long. This is what that looks like. So here we've got the edge of the top of the concrete. It is totally gone. There's a picture of Joe. He's on top of the tunnel, exploring what has now become this very large void above the tunnels. These voids can get quite massive. This had probably been going on for quite a period of time when we discovered this. So this void, at least in this location, extended for a couple 100 feet. We had to go down and explore these voids and understand what was happening here. It was part of our kind of learning process on how to deal with this tunnel system. The void here extended for well over 2,000 feet. It was about 6 city blocks, I believe, that the void was. We had to determine the extent of this void, so we had to follow it basically until the end and map out this void. Now, why are the voids important? So when we create the project, we are not only restoring the broken concrete of the tunnel liner, but we also have to restore that support structure around the tunnel. So we need to fill these voids. And in order to calculate quantities of material to use to fill the voids, we actually had to physically get into the voids and map them out, determine cross-sectional areas, and come up with our quantity calculations. So a lot of investigation happened not only in the tunnels, but outside of the tunnels too. One section of the voids, again, it's very coincidental that all of this happened pretty much in the same location that old time picture happened. This section of the void was probably 40 to 50 feet tall, probably similar measurements horizontally. This void we could easily have parked 2 city buses in. It had gotten to be that big over the 100-year period that this tunnel was in operation. So bring it kind of back to Central City. We had completed the 10th Avenue Tunnel project. We had completed the St. Mary's Tunnel project. Now was the Central City Tunnel system with its unique features and characteristics. It was a little bit different. We initially started looking at this in 2018, and initial estimates of correcting all these situations were running really high. $38 to $60 million was the range of estimates. So we spent quite a bit of time on this project. I'll turn it over to Joe at this point in time, and he can get more into the actual project, the Central City, and what we decided to do to manage this project. So I will
All
stop share.
right.
I'll stop sharing here if I can find the button. There we go. All right, take it away, Joe.
All right. So I'm going to share my screen. I hope everyone can see that. Um, So I'm going to pick up the presentation here, like Kevin described, and talk about the actual project of redoing, in a sense, our Central City parallel tunnel in 2021. We started before. I guess what I'm going to try to do is just give an overview of the progression of kind of the building of this tunnel, and show a lot of pictures and videos just to describe the project and what we did. As Kevin explained, after much inspection and assessment of our sewer system, we started on the road to prioritizing and rehabilitating and reconstructing our critical infrastructure. And Central City under our downtown was obviously very critical in nature. We'd been spending $500,000, sometimes $2 million maintaining this each year, and not to mention all the people down of our workers down there working in the winters just trying to maintain this. So we realized we had to do something. Our tunnel, the tunnels that run under Nicollet, Hennepin, Second Avenue, Marquette were typically they're about a three foot wide by 6 feet tall. So there's four of those tunnels running under our main streets, and they're all emptying into Washington Avenue tunnel, which was a 6 by 6 horseshoe tunnel. So if you do the math, if all those other 6 by 3 tunnels are full and they're running to a 6 by 6 tunnel down Washington, we had a huge problem, and we could only adequately handle about a 2-year rain event. So we realized we needed to do something, but we were in a very obviously developed area of town, the downtown, with little room for new access shafts, pits, or shafts. We had little room for new access shafts or ability to put down mining equipment. So we had to do a lot of preliminary studies on the best way to tackle the problem and how to address it. So here we eventually made a decision after quite a few years of using consultants and looking at the situation that we wanted to, instead of simply enlarging our old tunnel, which could be kind of problematic because rain events don't stop just because you're constructing a larger tunnel, we decided we would build a new, larger parallel tunnel. So this diagram kind of describes kind of what we were doing. Our old storm tunnel was running down Washington Avenue, and we are going to build an adjacent, larger parallel tunnel that could much better handle and convey that water to the river. So this would allow us to build in isolation much of the new tunnel while the old tunnel continued to work as it had been, and we could potentially work year round and decrease the project timeline and perhaps some of the costs of dealing with rainwater as we were working. So this diagram again shows, the old and new tunnel under downtown, how our drill holes from up above receive all the water from various catch basins and deliver it down to the tunnel down below. We had to put together an exhaustive decision and impact matrix to even decide, for instance, where to put our shaft so we could start working on this tunnel. And also some of the dewatering wells that Kevin mentioned. We basically have to dewater the sandstone that we're working in so that we can, in a sense, mine and then or put in the new tunnel liner. So we had an extensive matrix that we went through a long decision tree and process of trying to decide where we could even do and put any of our shafts or other dewatering wells. Plans and specs were put together, and eventually the project was put out to bid, and we contracted with PCI Roads to build the tunnel. And again, this tunnel is about 70 to 80 feet down below the surface. This diagram is what we shared a lot with the public, with the elected officials, residents, and businesses before we started the project, just to convey what we were doing, but also why we were doing it. So a lot of those pictures that Kevin shared we shared with them to show them the need for this project, that it wasn't just we just want to build a new tunnel, but there was a great need, and that our existing tunnel had served well over 100 up to 150 years, and we needed to do something to enlarge it. So this map here shows part of our old tunnel under Washington Avenue is listed there in the dark blue. And our new tunnel is in that lime green that runs along Washington, and it would go convey the water all the way down to Chicago and then out to the river outlet in the Mill Ruins Park area, if you're familiar with that, by the Guthrie Theater. We had room for one new shaft, which is that orange dot there on 2nd Avenue that you might see. And then we had 5 dewatering wells along the route to dewater the existing tunnel. And I will get to that in the next slide. So here, again, limited space downtown. That was some of our difficulty. We had to do water so that we do the work and make it basically a dry excavation to pour the concrete liner. We had room for 5 dewatering wells along the route, so about every 2 blocks. And our overall project length was about 0.8 of a mile. So every 2 blocks we had to dewater so we could draw down that water. And here is one of the dewatering wells on 4th Avenue. We started, so our project basically began in fall of 2021. Our first job was to dewater the project so we could start work. And here is on Nicollet Mall. This is another area where we started dewatering, and we found upon starting pumping the water that we were bringing in contaminated water, which is not unusual for Minneapolis. A lot of obviously our history in the past has allowed a lot of allowed a lot of contamination along the route. So we ran into contamination here, and the state required us to put down basically 2 large semi-truck filtering containers, basically actually two large settling containers, and then some large filtration devices that you see here. Luckily, this was the only location that we got contamination on the pumping. At our other locations, we would have not had room for this size of equipment, but it was a problem, and it was one that we had to deal with immediately. Otherwise, work could not have continued. So in the fall of 2021, besides putting in those dewatering wells, PCI was also starting the construction of the 12-foot diameter access shaft at 2nd Avenue in Washington. So basically what that involved was putting casing down through the overlying loose soil down to the top of the bedrock or limestone bedrock layer. And then the limestone, shale, and sandstone bedrock was cored into smaller pieces until they basically reached the depth of excavation for the new tunnel, which was about 75, 80 feet. And here's just the access shaft at 2nd Avenue then was set up with crane equipment, and personnel were lowered in to begin mining operations basically in the early winter of 2022. A large ventilation system had to be placed in there to provide adequate ventilation for the workers due to the equipment they were using down below and the dust. And basically the ventilation equipment created quite a bit of noise, and some of the things that we put up on the fencing, such as noise mats, did help in reducing the noise to the nearby businesses and residents. As you can see at 2nd Avenue, Washington, we were just close into a lot of people, whether it be businesses or apartment buildings, things like that. So here's a shot of basically the completed tunnel up above with the steel casing, but below they left it as unfinished sandstone until the very end of the project, which they eventually then did line and concrete. And here's a shot of that again from below, just bringing down the basket. The shaft was basically split into two, one to lower equipment or people in these baskets. The other half of it was, as you can see, part of those yellow ventilation pipes coming down. So in January of 2022, also so we were working at multiple locations. Basically this project allowed us to work at multiple locations. We did have an existing shaft also at Portland and Washington, besides the new shaft we're building at 2nd Avenue in Washington. So as you can see again in this picture, we're very close to a restaurant, apartments. We're in one lane of parking and traffic on Washington, very tight. But it is what it is. Being the type of project that we had to work in proximity to all this and try to be a good neighbor. And again, those noise mats and even the fencing banners made it a little more aesthetically pleasing, kept the noise down. And again, we were able to keep this new tunnel construction separate from the old tunnel so that we could work in isolation work all year long, which was a kind of a unique feature of this tunnel. So I'm just going to run through a few of the areas since we were working concurrently in a lot of areas. Here's the existing outlet you can see there in yellow. It's got a little red arrow pointing at it. Pretty small for the whole downtown district. It's right there by the Guthrie. So one of the areas that we then started construction on in the winter of 21-22 was right down here by the river. We had to remove that whole slope by the Guthrie Theater there and mine down, or basically take the soil out down to competent limestone so we could safely work on demoing the existing outlet and then start rebuilding a new outlet. So as you can see, this was just kind of in shaded red is just the area that we had to demo. A big obstacle that we had in this area was simply the various material that we ran across in this area. We had to get an easement from the park board, work with them, and then work with the various things we knew we were going to find in the slope from historic background of this area being a milling district. In the back there, you can see the old Washburn Crosby mill. The project called for the demo of the existing brick storm tunnel. This is a shot of that. And as you can see, I mean, it looks great. It's kind of cool, but if you can look closely, it's got basically a deformation in the brick where it's actually breaking apart. And it's this part of the tunnel used to be a combined sanitary storm, and it was showing its age. Had lived its life for over 150 years. It was built in the 1870s. In the fall of 2021, we started removal over that existing tunnel, and we had to end up removing more soil than we had intended to. And during that excavation, we ran into a lot of contaminated soils, such as asbestos. And in addition, we also had to dig back further into the slope. And when we did, we ran across this, which was basically a head race canal tunnel that carried water to Pillsbury mill that used to be right on this corner here. So that kind of made the project come to a screeching halt of sort. And we had to consult then, obviously, the state historic preservation to talk about what our next steps were. Here's just another shot of that top of that canal. It had basically braces across to hold it together, but as you can see, it was filled with debris from what ended up being roughly from the 60s and 70s. Any adjacent building nearby, decided to use this as a place to pile all their demo debris into, which didn't help us either because we had to deal with part of that too. So again, huge challenge with all the contamination and things we found here, and working with the historic society and whatnot. So some obstacle. And here is again, now as we started construction, was we took away some of that slope, we had to put down some tunnel shotcrete on the slope to keep it from falling into the workers, and a cofferdam was put up, and there you can see the size of the outlet. It's pretty small. It was not huge, and so it was not allowing the water to escape quickly, thus causing some of that, basically like a backed up water hose. It was just causing pressure all the way up the system. Here's basically a little video that was just showing some of the excavation that we had going on here at the outlet, just to give you a little taste of what was happening here. They have basically mined part of this, and they have basically some mesh and rock bolts to hold the structure up from above, and they're just tapping out some of the sandstone. And here's again another shot. This is looking from the river up into that same tunnel I was just showing you from the river. We had two tunnels. The one on the right here is the tunnel that takes all the water from downtown Minneapolis, from our oldest central city. And the tunnel on the left is from Chicago Avenue. So basically this outlet is providing an outlet for two separate storm systems. This picture basically shows what was happening, or what we were able to do with our construction. So we had the new shaft right here at 2nd Avenue. We were able to mine this way, and then they would mine this way all the way down toward Portland. This is our existing shaft at Portland. And they kept this in isolation, and they were able to mine this way toward Chicago. And then the outlet that I just showed you, they were able to mine this way. So we were able to work in at least four different directions at the same time, which helped get some of the work done more quickly. I'm just going to show you a couple of shots here of some of the cutter. It was not a big tunnel boring machine, tunnel mining machine. It was simply almost like little rotating heads, and I'm going to show you a video clip in a second here of this, but it just worked away at scraping away the sandstone, which is somewhat easily mineable, and the sandstone layer lies underneath a limestone bedrock up above. So that limestone above gave a kind of a competent bedrock to mine up until. And here they're just using lasers, like you can see the mesh on the wall and the rock bolting to protect the workers while they're working. And they're just using lasers here. They're making basically a cathedral shaped tunnel. And here's, again, they're just hauling out with very small equipment. And I'm going to give you here's a video, again, an example of how it's mining. So it wasn't a fast process. This is just, again, they would just literally be scooping up some of the sandstone as they're working, scoop it away. They'd be mining concurrently at the same time, but it was not a super fast process. Here is this, we had different, depending on the geology. So we have that, like I said, the limestone layer lying over the sandstone, and the limestone would dip and dive at times. So our shape of our tunnel varied from a cathedral, which they had just been mining previously in that slide, to some of various box sections. So we had to work within the confines of the geology to make this work. So you would mine up to the limestone, but that made our shapes and our tunnel change over time. And as we were adding more water input from various streets, we would have to enlarge the tunnel for volume wise capacity. So here we have this is the double box section. If coming up here. And if you can see again, here is the Central City Tunnel opening of the old tunnel and the Chicago Tunnel. And so they've mined the walls in this double box section with a poured invert. The walls obviously aren't done yet. Here they're just coming through with their form, and this is how they would basically pull this form along and pour the concrete walls and then the ceiling above. Here, this shows just a section of that double box section, just with finished sides and floor next adjacent to unfinished rebar. So they'd always just work in progression, rebarring, and then pulling that form along, and eventually pouring a new form in the next week. This is a shot of again at the outlet where they're getting near done. You can see a little part of that old section of that old outlet there in the foreground or background, and they're working though on the new tunnel section. Here's a shot looking from above. The old outlet is there to the left, and the new outlet that's been done, and they're eventually going to be meeting this and demoing this last section. So this is all at the outlet. There's again a shot of the shotcrete that they had to put on the soil around that area to protect the workers. And then also here you can see this was an old railroad pier that we also had to work with these historic items and not damage them. And so that was also obviously a challenge besides the contamination we found in the area and the head race tunnel. This again a shot now when that outlet was done. They just started putting new soil on there, and you can see the Stone Arch Bridge and where we are in relation to the Mississippi River. Again, here's just another box section, different part of the tunnel. I'm just going to show you a few pictures and try to get through this. This is where they mined it. They put up the mesh and the rock bolts, but no concrete had been done yet. This is kind of by Portland Avenue in Washington. You would see that they use some rails here to basically haul out some of their mined sandstone. And then you see the ventilation pipes on the ceiling there that were providing ventilation, but also a problem at the surface because of the noise for the machinery to do that ventilation. This is a section kind of by the curve where Washington Avenue then curves toward Chicago. This is kind of right at the Guthrie Theater. So this section of tunnel, you can see basically the rebar put in the floor, and they're basically using a screed. This screed here would spin around, and they're using the guides of this wooden form right here to pull that screed across to form the concrete floor. So it was really a neat invention and use of this to make a really nice finished floor that had a slight curve to it. And there you can see in the bottom here that screed that's kind of curved as it spun around. Here's just a shot of it showing the obviously it cured, and then you have basically a poured curb wall, and then you would do the next section. When you pull that form across, you would do these walls and the ceiling or the crown. Let's see here. I gotta get rid of this pointer here so I can. And this is again just a different part of it now being finished. Just kind of give you an idea of how massive this thing was. Various sizes, 12 by 12 at times, 12 by 8. By the outlet is 20 feet wide by 12 feet tall. So just a very long, large tunnel. Again, in the very upper part of our tunnel near Washington Avenue in Nicollet, we did a cathedral. We didn't need it, the tunnel as big at that point because we didn't have as much water flowing in to that new tunnel at that point. So just a different shape. This just shows you the various shape and then the size of how they did that tunnel with, again, a similar form, but it's cathedral shape. So. And then a shot of the tunnel being finished that way. And then finally we connected the tunnel at roughly Portland and Washington. That was our final phase. And this is the existing tunnel or the existing shaft that we had at Portland Avenue. We had to work around that, rebar it up, and then connect the two tunnels and in a sense make it live. At this point, the new tunnel was open to groundwater and to the old tunnel system, so we had to work carefully and around the weather. And this is kind of shows the massive connection point there at Portland Avenue. You've got basically some of the old tunnel sections that are crisscross and meeting this new tunnel section here that is going this way. And then what we also did is we wanted to interconnect the old and the new tunnel together so that as the water levels rise, they would rise together and provide the largest amount of capacity for our rain events. So this is our old tunnel here. This is a tunnel that typical tunnel size, 3 by 6, that goes down Nicollet and Hennepin, 2nd and Marquette, and then it's tying into the new tunnel that's over here. Again, there's some connections, and this is a drill hole. This is the water coming down from the catch basins and a drill hole, basically 16-inch, 24-inch drill holes that came from the surface. And then these are some of our interconnections between old and new tunnels. And this is a shot of as we're getting near completion of the outlet. And that was just again, just to give you a little feel for some of the construction that we had. Things that we learned, expect the unexpected, like the contamination, be ready to act and have a plan in place, work with 70 feet down below. So work didn't happen real fast, and communication to the residents was, and to the elected officials and businesses was key. So we were, one way that we did that, we made these banners that I said I described that we put on our fences, and they gave a little bit of information about what the project was, maybe a map of things, and some old pictures from when the original tunnel was built, just to give a little flair and to make it look a little better aesthetically. We would have a QR code and a website so people could find out about the project with their cell phones and make communication and link them up to our website if they wanted. And this picture is just a funny story. We tried, we worked with a company to put up these fence banners, and we went back and forth, and they kept putting this picture in there as one of the final pictures for the project. And I kept saying to them, I don't think this is going to work well with a man being carried out of the tunnel. So probably 3 times it took me to finally to get them to take this picture out of there, because I didn't think it would convey a very good story for our tunnel. And lastly, these are the quilted mats that were noise barriers that reduced the decibels from our project sites that we had in the city, and it helped quite a bit. So lastly, I'm going to leave you with a few-minute clip that we had WCCO and Star Tribune come down to our tunnels, and they both did great stories, and I'm just going to try to play that for you. You're going to get a little, it's coming from YouTube, so we might get a short little commercial at first. Let me try to roll that.
You hearing it, Joe? There's no sound.
Still no sound.
No sound?
Nope.
Yeah, you have to share with audio on Teams for the sound to come through.
How do I do that?
So I believe you'd actually have to unshare and
What's
then
that?
reshare. I believe you would have to unshare and then reshare your presentation with sound, but it's also for after
Sorry.
the top of the hour.
Okay. Yeah, sorry about that. I apologize. I hadn't had a problem with the sound in the past, so it is something you can
There's a link.
go out. Yep,
Yep,
there's
they
a link.
posted a link. The link's in the chat.
Oh,
Oops,
perfect.
sorry. Okay, so that ends that portion. I apologize for that, for not for the sound not working.
That's okay. No worries. I saw Kevin was going through the chat and answering questions. I do want to be respectful of everybody's time. I think the only question that wasn't answered was what you guys did with all of the sand that you were removing from the tunnel. Oh, nope. You did get to that one too. It was disposed of. Okay.
Yeah, and the sand went to McCrossan, who owns PCI. So what they did with it at that point, but it makes great golf course bunker sand. But it was a massive amount.
Yeah, I'm sure. All right. I think that was it for our questions. This was, as expected, an incredibly interesting presentation, just fascinating stuff. I did see Emma asked if there's any way to get a tour of the tunnels if you're not the governor or a city council member.
You know, if we, I mean, it is like I talked about it. I mean, it is quite an effort to put together staff to support a tunnel tour. It's cranes, it's traffic diversion, it's stuff like that. But if we get enough people interested, we can make it happen.
All right. Mark and I might have to follow up with you on that.
That'd be an on-site water issues seminar.
Yes, exactly. The first ever.
If someone offers to bring pizza, then we can really make it happen.
I think we can.
At least one pizza.
Yes. Yeah, absolutely.
That's absolutely fascinating talk.
Great.
Yes. Thank you so much. Have a good rest of your Thursday, everybody, and we will see you next time.
Sounds good. Thank you.
All right. Thank you.
Thanks.